Section 14 is about normal subgroups and factor groups, and this is probably the most difficult section in the textbook. It gets easier after this section. So let's start with some motivation for normal subgroups and factor groups. So in general, groups, especially non-abelian groups, can be complicated. And to understand them, by which I mean classify them, for example, asking how many groups of order 20 are there, it's useful to break them into smaller groups, analogous to how molecules are made out of smaller molecules. Now, a normal subgroup N, I'm not giving the definition just yet, but it has a certain property that we can form a group G mod N, called the factor group or quotient group, that's what's part of the title here, out of the set of left cosets of N. Now, when N is normal, the left cosets are actually going to also be the right cosets, so that's why I put left in parentheses. And the point is, we can think of the group G as being built out of the two groups N, which is a subgroup, and G mod N as a factor group or quotient group. And so this goes back to the idea of how molecules are made out of smaller molecules. This group G is made out of the smaller group N, and not a subgroup G mod N, but a quotient group or factor group G mod N. And the hope is that since N and G mod N are in some sense smaller, maybe they are better understood, and we can use that information to better understand the group G. And this idea of understanding a complicated mathematical object by breaking it into simpler pieces is a common theme in math and science, and leads to notions like direct product, which we've talked about, a semi-direct product, extensions, short exact sequences, normal series, filtration, spectral sequences, and cohomology. Now, these terms are terms we won't talk about in this course, but if you go further along in algebra, you'll definitely see them. So here's the definition of a normal subgroup. So let G be a group and H be a subgroup of G. Then H is normal, or normal subgroup, if for all elements G in the group G and H in the group H, subgroup H, that this strange combination G, H, G inverse is also in H. Equivalently, G, H, G inverse is a subset of the subgroup H. This combination G, H, G inverse is sometimes called the conjugation of H by G, or the conjugation by G of H. It seems strange when you first see it, but because it comes up so often in group theory, it's given a name called conjugation. Okay, now if H is a normal subgroup of G, we write H triangle like so, G. Let's look at some examples. Well, in an abelian group G, every subgroup is normal because this condition, GH, G inverse, lands back inside the subgroup H when you start off with an element of your subgroup H. Well, that becomes GH, G inverse. Well, you can interchange the order of H and G inverse, so to get G inverse H, and again, that's when the group is abelian. Abelian means commutative, and so you can change the order. And then G and G inverse, they cancel out, and we're left with H, which obviously is in the group H, since that was our starting assumption. So in an abelian group, every subgroup is normal. What makes groups complicated is that they're non-abelian. Some of them are non-abelian, and so that's why the notion of normal subgroup is to distinguish from arbitrary subgroup is important. Now, another example is the kernel of any homomorphism of groups is a normal subgroup. That's what this next theorem is saying. So let F from G to G prime be a homomorphism, and the kernel of a homomorphism is the elements of G, the domain side, that map to the identity element on the target side. So that's the definition of kernel. Let's let H be the kernel of a homomorphism, and we'll prove that H is a subgroup somewhere else. that's not what I want to focus on now. I want to focus on showing that H is a normal subgroup. That means it's stable under conjugation. So we have to show that for every G in G, every H in H, that this conjugation, this GHG inverse, lands back inside H. Now, H is the kernel, and that means the set of elements of the group G that F sends to the identity. So to show GHG inverse is in H, we have to show that F sends GHG inverse to the identity element of G primed. Okay, so let's compute what F of GHG inverse is using the fact that F is a homomorphism. And what that means is that you can split up or distribute F along each of the factors of your product. So F of G times F of H times F of G inverse. And F of H is the identity element since H is in the kernel. So F sends H to the identity element. We've seen in a previous video that if F is a homomorphism, F of G inverse is the same as F of G quantity inverse. So you can move this inverse outside. And then the F of G and F of G inverse cancel, and you're left with the identity element of G. And so indeed, F sends this element to the identity element of G primed, and so therefore this element is in the kernel, and that concludes the proof that the kernel of a homomorphism is a normal subgroup. And we'll see that every normal subgroup arises in this manner as the kernel of some homomorphism. Let's use the theorem we just proved, that the kernel of any group homomorphism is a normal subgroup, to cook up some more examples of normal subgroups. So let GLN, GL stands for the general linear group, with entries in R, be the set of matrices that have non-zero determinant. Set of n by n matrices, that's what this notation refers to, with entries in R. And this is a group under matrix multiplication. This condition that determinant of M be non-zero means that a matrix will have a multiplicative inverse, or just an inverse is what you call it in linear algebra. And so therefore it satisfies one of the conditions of being a group, that is the existence of inverses. Now let's make a homomorphism called det. I wrote det, short for determinant, that sends a matrix to its determinant. So I give an n by n matrix, and the output is a real number that's non-zero because of this condition that we're only looking at matrices whose determinant is non-zero. And R cross is how I denote this, or R times. This is as a set, it's all the non-zero real numbers. As a group, the group operation is multiplication of non-zero numbers. Okay, and so this determinant map is in fact a homomorphism. This is a fact from linear algebra, that the determinant of a product of two matrices is the product of their determinants. And so we have a homomorphism of groups. Again, the group operation on R cross is multiplication. And then let SLNR be basically the kernel of this homomorphism, namely the matrices, the n by n matrices, whose determinant is 1. Remember that this here is a multiplicative group whose identity element is 1. And so that's why we're looking at matrices that under this map get mapped to the identity element. Okay, SL stands for the special linear group. These groups, GLN and SLN, are very well studied and appear in many places in Lie group theory or in algebraic groups and so forth. So what we have is that the kernel of the determinant function is the special linear group, and so therefore by our theorem, the special linear group is an example of a normal subgroup of GLN-R. Okay, and so what's the point? Well, that means that the GLN-R, this group of matrices, is built out of this group SLN, the matrices with determinant 1, and the quotient, which I haven't written here, but it turns out that the quotient of GLNR with SLNR is R cross, this group R cross. And so GLNR is built out of two smaller groups, SLNR and R cross, and to study GLNR, you can study the SLNR and the group R cross, which is much easier to understand, of course. Let's do another example. The alternating group AN is a normal subgroup of the symmetric group on n letters, Sn. And why is that? Well, there's a homomorphism called the sign homomorphism that goes from Sn to the multiplicative group of plus or minus 1. That sends even permutations to 1 and odd permutations to negative 1. And it's a fact that this sign map is a homomorphism, and the kernel then is, well, the elements that map to 1, and those are the even permutations, and AN, the alternating group, is exactly the set of, or subgroup of even permutations. It can be a little bit hard to get a feeling for what these normal subgroups of a group are. Let's look at SAGE and ask for it to compute some normal subgroups. It has a built-in command to do so. So here I've defined G to be the symmetric group on 5 letters. So in our typical notation, G is S5. It has 120 elements. And then if I ask this G.normal subgroups, it's a built-in command, and it lists the normal subgroups of G. The output here is a bit hard to read, so I've made a for loop that lists out these groups on each line, on a separate line. So let L be the list consisting of G.normal subgroups, and then as I run through the elements of L, I print them, and okay, so this first element is a subgroup generated by the transposition 1, 2, and the cycle 1, 2, 3, 4, 5, and it turns out that this subgroup is actually the entire group, S5. It's not so easy to see that. That's not obvious. But you can actually ask Sage to do that, to compare this subgroup to S5, and it'll say, yes, it's indeed S5. Okay, and then the second subgroup, the group generated by 3, 4, 5, and 1, 2, 3, 4, 5. So these both have these are cycles of odd length. This is a cycle of length 3. This is a cycle of length 5. And so those are both even permutations. And so this subgroup is going to consist of even permutations, and it turns out that it is all the even permutations. That's, again, not obvious. But the subgroup is A5, consisting of all the even permutations. And then finally here, this last subgroup is generated by just the identity element. This is the notation for the identity element, the empty cycle. And so that's what we have here. That's a normal subgroup in any group. Okay, and so what we have is that S5 is built out of A5, and the quotient, it turns out that this quotient group, which I haven't defined, consists of just 2 elements, and so it's a cyclic group of order 2. For example, written additively, it's 0, 1 with addition. And the structure of S5 is the reason why there's no general formula for the quintic. In other words, a degree 5 polynomial. There's no general formula for its roots. Unlike the quadratic formula, it gives the formula for the roots of any quadratic or degree 2 polynomial. There's no such formula for degree 5 polynomials. And the structure of S5 is the reason why. Now, our goal in this course is to explain exactly why that is the case. Again, it's not obvious at all. And it was one of the motivating questions of the rise of group theory.